Hello everyone, I am Dr. Chalapathi Rao, Associate Professor, Department of ECE at VJEC, Hyderabad. Today I am going to discuss about the high-pass RC circuit for sinusoidal and step input signal response in linear wave shaping circuit. So high-pass RC circuit. So here this is the circuit. Here there are two components are used. One is capacitor and another one is the resistor. The capacitor is connected in series and the resistor is connected to the ground. The output voltage across the resistor. So here the capacitor is the reactance of the capacitor. It is a frequency dependent of its reactance. At zero frequency, the reactance of the capacitor FC is infinity, and so it blocks the input and hence the output is zero. This capacitor is called the blocking capacitor, and this circuit also called the capacitive coupling circuit is used to provide DC isolation between the input and the output. So this circuit attenuates low frequency signal and allows transmission of high frequency signals with little or no attenuation is called the high pass circuit. Now at zero frequency, at F equal to 0, so the reactance of the capacitor X is equal to 1 by 0. So here the reactance of the capacitor is 1 by omega C, where omega is equal to 2 pi F. So 1 by 2 pi F C. So now at F equal to 0, the reactance of the capacitor is infinity. If the reactance of the capacitor is infinity, circuit is open. If the circuit is open, there is no current flow through the circuit. So the output across the resistor or V0 is equal to I into R, where I is equal to 0. So therefore V0 is equal to 0 and gain A is also 0. So here the gain is output by input. So here input is if any input signal, the output value is 0. Now if F is increasing, now the reactance of the capacitor is going to decrease, the output voltage is going to increase, V0 is going to increase and gain also going to increase. And the third case, so here we need to define the cutoff frequency. So the cutoff frequency is defined as the frequency at which gain is 1 by root 2 of its maximum value. Here the gain is increasing 0 towards to maximum value. Here at F equal to FC, cutoff frequency, the output is the gain is 1 by root 2 of its maximum value. The maximum value is 1. So here 1 by root 2 is 0.707. So and after cutoff frequency, that means if F is very high value, if F is infinity value, the reactance of the capacitor X is equal to 1 by infinity. So that is equal to 1 by infinity is equal to 0. The capacitor is short circuit. It acts as a short circuit. The entire input voltage appears at the output. So therefore V0 is equal to V in and gain is equal to 1. So this is the graphical representation of high pass RC circuit. So frequency versus gain. So for low frequency signal, the gain is 0. So for very low frequency signal, gain is 0. So now frequency is increasing, gain also increasing up to maximum value. At F is greater than FC. So after cutoff frequency, gain is equal to unity because output is equal to input. So here, so after cutoff frequency is the pass band, before cutoff frequency is the stop band. Now the sinusoidal input response of the high pass circuit. So here, if the input voltage is sinusoidal VI of t expressed as VI of t equal to Vm sin omega t, applying KVL to the circuit. So here the input voltage VI of t is equal to voltage across capacitor plus voltage across resistor. So voltage across capacitor is 1 by C integral of I of t dt plus voltage across the resistor is R into I of t. So this is the equation number 1. Now taking Laplace transform on both sides, taking Laplace transform on both sides with 0 initial conditions, Vi of t Laplace transform is Vi of s is equal to 1 by c into integral of I of t Laplace transform is 1 by s into I of s plus r into I of t Laplace transform is I of s. Here I of s is common, 1 by cs plus r. So can write this I of s into, so denominator is cs, so 1 plus rcs. From this equation, I of s is equal to input voltage Vi of s by 1 plus RCS by CS. Now you can write in numerator CS. So this is equation number 2. Coming to the output side. So the output is across the resistor. So here V0 of t is equal to voltage across the resistor R into I of t. So this is equation number 3. Again taking Laplace transform on both sides. We get V0 of s is equal to R into I of s. So this is the equation number 4. Now, so here from equation 2 is I of s. So equation 4 is V0 of s into R into I of s. Now substituting equation 2 in equation 4, we get V0 of s is equal to R into I of s, where I of s is equal to Vi of s into cs by 1 plus rcs. So that is equal to Vi of s into rcs by 1 plus rcs. Now here the gain or transfer function is V0 of s by Vi of s. So V0 of s by Vi of s is equal to rcs by 1 plus rcs. It is denoted by the transfer function h of s. So here we can write s into rc by 1 plus s into rc. Now here numerator and denominator s into rc is common. So finally we get 1 by 1 plus 1 by src. So this is the s domain function. Now in frequency domain, s replaced by j omega. So here h of j omega is equal to 1 by 1 plus 1 by j omega rc. So where omega is equal to 2 pi f. So 1 by 1 plus 1 by j 2 pi f rc. So you can write this 1 by, so 1 minus j by 2 pi f rc. So this is the gain function. Now coming to the frequency responses. See here we need to derive magnitude and phase responses. The first magnitude response is mod A is equal to 1 by square root of real part square plus imaginary part square. Here 1 square plus 1 by 2 pi f rc whole square. So this is the magnitude response, and the phase response theta is equal to minus tan inverse of imaginary part by real part. Here the imaginary part is minus 1 by 2 pi f rc by real part is 1. So minus tan inverse of minus theta, that is equal to, you can write tan inverse of 1 by 2 pi f rc. So this is the phase response. Now at lower cutoff frequency f1, so here in the high pass filter which allows the only high frequency signal and stop the low frequency signal, here we get the lower cutoff frequency, and upper cutoff frequency is the here which allows the very high frequency signal also. So that's why the upper cutoff frequency is infinity. So here the upper cutoff frequency f2 is equal to infinity, and f1 is equal to lower cutoff frequency is cutoff frequency only fc. Now the bandwidth is equal to f2 minus f1, so that is equal to infinity minus fc is equal to infinity. In high pass RC circuit the bandwidth is infinity. So now at a lower cutoff frequency f1 the gain is 1 by root 2. So here the gain mod A is equal to 1 by square root of 1 plus 1 by 2 pi f RC whole square. Now equating this to 1 by root 2 is equal to 1 by square root of 1 plus 1 by 2 pi f RC whole square at f equal to f1. Now squaring on both sides and cross multiplication, 1 plus 1 by 2 pi f1 RC whole square is equal to 2. So 1 by 2 pi f1 RC whole square is equal to 2 minus 1, 1. Square root on both sides. F1 is equal to, we get F1 is equal to 1 by 2 pi RC. So this is the lower cutoff frequency. And coming to the magnitude and phase responses, so mod A is equal to here 1 by 2 pi RC is equal to F1. So 2 pi RC is equal to, we'll get 1 by F1. So now here replacing 2 pi RC replaced by 1 by F1. So finally we get mod A is equal to 1 by square root of 1 plus, so 1 by 2 pi RC, 1 by 2 pi RC, that is equal to F1. So F1 by F whole square. And the phase response theta is equal to tan inverse of, so 1 by 2 pi RC is F1 by F. So these are the more magnitude and phase response of the IPAS RC circuit. And the graphical representation here, so the magnitude response mod A is equal to here 1 by square root of 1 plus F1 by F whole square. Okay, here if F equal to 0, F1 by 0 is the infinity square is infinity plus 1 is infinity. So the denominator is infinity. 1 by infinity will get 0. So gain is equal to 0. At low frequency signal, gain is 0. Now at F equal to F1, so F1 by F1 is 1. So 1 square plus 1. So square root of 1 plus 1, that is equal to 2. So 1 by root 2. So 1 by root 2, that is equal to 0.707. At very high frequency signal, that is if f equal to infinity, so f1 by infinity will get this 0 square plus 1 only. So square root of 1, the denominator and numerator is 1 by square root of 1, that will get 1. So here the for a high frequency signal, the gain is unity. So this is the sinusoidal response of the IPAS RC circuit, which allows the only high frequency signal and stop or attenuates the low frequency signal. Less than cutoff frequency is the stop band. Here this is the stop band, and greater than cutoff frequency is the pass band. So this is the response of IPAS RC circuit for sinusoidal input. Now the step input response of the IPAS RC circuit. Consider the step input voltage of magnitude V is applied to the IPAS RC circuit having a time constant RC. A step voltage VA of t can be mathematically written as VA of t is equal to V volts for t greater than or equal to 0, 0 for t less than 0. So this is the graphical representation of input signal. So here t greater than or equal to 0, the input voltage is V volts constant. For t less than 0, the input voltage is 0. So the voltage across the capacitor cannot change instantaneously. The output voltage will be just equal to the input at a t equal to 0. For t less than 0, VA is 0 and also V0 0. Later, when the capacitor charges exponentially, the output reduces exponentially with the same time constant RC. The expression for the output voltage for t greater than or equal to 0 is given by, so V0 of t is equal to V final minus V initial into e power minus t by RC. So here the output is exponentially decreasing towards to 0. So here the initial value is V volts and the final value is 0. So therefore the final value Vf is equal to 0, and V initial value V initial is equal to V volts. So the output voltage V0 of t is equal to V naught of t is equal to V final 0 minus V initial is V volts into e power minus t by RC. So that is equal to, we'll get minus of minus V, that is V into e power minus t by RC. So the output response is based on the time constant. If the time constant value, RC value is very large value, so the output is slowly decreasing towards to zero. Slowly decreasing towards to zero. Suppose if the RC value is small value, now it will exponentially decreasing towards to zero slightly. And if the RC value is very small value, the output is suddenly, that is very quickly down towards to zero. This is also in the form of exponential. So this is the step response of the high pass RC circuit. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.